Continuing to learn about logarithms, one of the most important type of logarithms is using a very special number. So we're going to deviate a little bit to make sure we understand where this number comes from. Something we're going to learn later is using logarithms and exponentials to compute how money grows when it's being compounded regularly with an interest rate. This is our formula for compound interest. Okay. We are going to cover this later in the application section, but just quickly, A is the amount at the end. Okay. P is what we call the principal, or the amount you put into the account. R is the interest rate. T is the number of years that you're leaving your money in the account. And N is the most important thing. It's the number of compoundings per year. So are you compounding it quarterly? So N is 4, monthly, so N is 12, so forth. Now an interesting thing happens. For simplicity, we're going to let these three middle ones equal 1, just because it's the easiest number to plug in. And we're going to say, I don't really understand what N is, so what happens as N gets bigger and bigger and bigger? Because if you compound your money more often, you make more money, because your interest is earning interest quicker. So the logical thing to say is, well, if I compound it often enough, I can make however much I want from $1. Only that's not exactly true. What happens is if you plug in the 1 for all of these and let N go to infinity, the amount approximates this number called E, which is 2.718, so forth. Okay. It's a number like pi that's irrational, so we can't just write it down as a fraction or anything, which is why we just call it E. So E is such an important number that the log base E of x, we don't tend to write as log base E, we write ln of x, meaning natural log, but in French, so the letters are reversed. There's another special logarithm, and that's log base 10. And log base 10 is important because our number system is base 10. And so log base 10, we just don't write a base. So if you just see log of x, you know that the base is actually 10. Now, before we get to any kind of computations, I want to point out a very important warning, warning number 19. It says that you cannot separate the logarithm from the thing inside it. Okay, so just looking at what's going to be our first example, I cannot separate this log from the 1000 unless I'm going to be using the property of the fact that exponentials undo logarithms. This is not multiplication. So I cannot just divide both sides by logarithm and be left with the 1000. Okay? So be very careful of that. Now, I'm going to compute what these logarithms actually equal. So this first one, I know, well, there is no base. And when there is no base, I know that it really means base 10. Now, here's what you want to do if you want to actually compute what a logarithm equals. You want to try to write the thing inside the log as a power of the base. So can you write 1000 as a power of 10? You go, yes. So this is log base 10 of 10 cubed. Now, if you remember, when we first introduced logarithms, we say they are inverse functions of exponentials, meaning if we did one followed by the other, it's like nothing happened. So log base A of a to the x just turned into x. And that's the situation we have here. Log base 10 of 10 cubed is just that 3. I'm going to try the same thing here. Again, there is no base, so I know that means it's really base 10. Now I want to write this thing inside the log as a power of 10. And square root is really 1/2 power. And then because it's log base 10 of 10 to a power, this just equals the power of 1/2. Now one more example. This is log base 8 of 2. And you say, well, I don't know how to write 2 as a power of 8. But if you take a step back, I know how to write 8 as a power of 2. So off to the side, I'm going to say 8 is 2 cubed, which means that 2 will be the cube root, or 1/3 power of 8. So this must be log base 8 of 8 to the 1/3, so it equals 1/3. Now one last thing we want to do, we want to be able to translate from one to the other. So if it starts out as a logarithm, I want to be able to translate it to an exponential. Now remember, when there's a no base, it must be a base 10. So log base 10 of 7 equals 0.845 tells us that the exponential base 7 with exponent 0.845 must equal that 7. So both of the bases are 10, but which number I'm solved for switches. So here I was solved for the 0.845, here I was solved for the 7. And the reverse happens when we translate to logarithms. So this is an exponential base e, so it will be a logarithm base e, or a natural log. And instead of solving for the 7, I'm going to put the 7 inside and solve for the 1.94591. Okay, so logarithms and exponentials, they undo each other, but they also turn the problem on its head. Whatever was inside becomes outside, and vice versa.